So let me give you a little bit more detail about absorptive arrival times. So remember, the idea here was that we replace the standard time evolution operator of quantum mechanics by an operator that, by a semigroup that can be written as e to the minus I k t over h bar. And so this is a contraction semigroup. Each CT is an operator of norm less than 1, but that's also called a contraction. So this is of course just also a semigroup. So this is a contraction semigroup, a semigroup of contractions. And this, so for example, you could do this by taking a generator for this contraction semigroup to be your good old H, and then you subtract an operator and M is positive. So this is now not a Hermitian operator, but if that is a positive operator, it will generate a contraction semigroup. How do you actually see that the norm is less than 1? Because of course you would have this in the exponential, and you know that you cannot just pull the exponentials apart. But actually you can in the Trotter product formula. So if you have two contraction generators and you add them up, then the Trotter product formula, which makes it in small time slices, shows you that this should be a contraction semigroup. Right? Now also, actually in the examples I will give, often M is more singular than that. Huh? So I'm suggesting here that M is a bounded operator, maybe. It could be unbounded, all right, but it could even be something as weird as the delta potential. Now, by itself, this is not even an operator, right? Because it multiplies a wave function. When you multiply a wave function by it, then you get something which is a delta function, proportional to a delta function, and that is ill-defined in any sense. So that really doesn't make a good operator. Technically speaking, you would say this can be defined as a quadratic form, but it's not even closable. So this is a very bad operator. But as you know from the case where I don't put an I here, where you just add a delta function potential to a free time evolution, there it makes perfect sense. So actually the domain of the Hamiltonian, on the domain of the Hamiltonian, you can define this sum. And that is also true for this case. So rather singular examples of such M's will appear, right? So that we'll see later in our examples. And some of them are perfectly natural, right? So no reason to exclude them just because they're not bounded operators. So now the time observable that goes with it, we already wrote down, right? So t, let's say s, so t is smaller than s here, will simply be the Ct star Ct minus Cs star Cs. So actually, because it's a contraction semigroup, this is smaller than that. And so this is actually a positive operator. And it's also, because it's a difference, it's clear that these add up over intervals, right? So the middle term will just drop out. So this produces a measure. And if you look at the expectation value of this, so actually psi f psi, right, is simply the norm of Ct psi squared minus the norm of Cs psi squared, right? And because it's a contraction semigroup, this one has to be smaller, so it's a positive expression. So the loss of normalization is really interpreted as arrival. That was the whole idea. Huh? Now, it will be one thing that we want to do is to develop a very flexible modeling scheme. So if we have a detector described by M and another described by another M, let's say M1 and M2, right? You want to describe the combination of the two counters. So you could naturally just add these guys. But then obviously you want to know where did the particle arrive. Right? So my next aim is to give an explanation of how can I understand what happens upon arrival. Is it this detector or is that detector, or maybe something more complex? Okay, so that's the next step. So the loss of normalization under such a contraction semigroup is interpreted as arrival. So let us look in more detail, like where the loss happens. And the way to do that is to note that, so K is now an unbounded operator, right? So that's a contraction generator. And I don't care how it's related to some possible Hamiltonian. We just take the K, right? And so I write dom K for the domain of K. So actually that would be the set of vectors, so that if you take the contraction semigroup, subtract what it is, t equal to 0, divide by t, apply that to psi, then there is a limit which you then call k psi. So this goes to 0 as t goes to 0. So this is the set of vectors on which this derivative formula makes sense. Okay, so whatever that is, I would like to study the normalization loss on that. Now, the normalization loss on such a vector psi is the derivative of ct psi, and it's of course convenient to square that, right? Let's look at that. Now, this is going to be a negative quantity because we're looking at a contraction semigroup, so I'll put a minus sign. Now, this is the derivative of ct psi, of course. Now, assuming that psi is in this domain, we can actually do the derivative factor by factor. So this is equal to minus, that's the minus sign out there. Now, if we take the derivative of ct, just as a reminder, ct is equal to minus itk over h bar, right? Then we have to just have to put this in, right? The derivative is minus ik over h bar, so we can pull out a minus I over h bar. And then we have k psi minus psi k psi, and I may have to adjust the sign. So minus sign, here we have a minus sign as written, that's okay. Okay, so this is an expression which is actually bilinear in psi, and it's also positive, right, because we put the minus sign there. So it is like a scalar product, and that is something that we're going to take seriously, right? So I will. So with this scalar product, you can actually also define it then for different arguments, right? And so define a Hilbert space E, the exit space, as the completion of dom K with this norm, this as a norm. So we turn the normalization loss and a vector in that domain, we turn into the norm of the vector. Now, then what you basically do is you take you make this, well, you use this as a norm. You make Cauchy sequences and identify equivalent ones. So actually, if you have a vector in the domain, then you can take the constant sequence. That will be converging because it will just have, I mean, it's obviously a Cauchy sequence. So that is actually the embedding of, I call this little j, of the domain of the generator into the exit space, right? And the formula that defines this is the scalar product is this limit. So actually, we know that j phi, the scalar product, that would be then the scalar product of vectors, of the embedded vectors, is just minus d by dt ct phi ct psi. Right? If you really define E as the completion, then every vector, the exit space is generated by such vectors. So the image here is dense. Right? But sometimes we actually allow non-minimal exit spaces where they. But this formula is something that we just stick to. So this is the scalar product in E, of course. Right? So I don't usually write that, but just to make clear that this is the scalar product in E. Okay, so this is an interesting Hilbert space, and we'll analyze that a bit further. So we use this exit space now to build another operator. Namely, this is going to be, I call this capital J. That's capital J for me. And this takes the original Hilbert space into a space of square integrable functions on the positive real axis, which we interpret as the time. And it takes values in the exit space. Okay. So, so this is my notation for that kind of space. And the definition of it is that if phi is actually in this domain, then j phi, now this is supposed to be such a function, so I have to give you the value of the function, right? So at time t is equal to the little j that we defined before applied to ct. Now, if phi is in the domain, then ct phi is also in the domain. It doesn't matter on which side of the interval you differentiate. So, so that is, this is also in the domain. Therefore, this produces a vector in E, and that is the value of this wave function. Okay? So, I claim that this is a nice bounded operator, even though K is unbounded and all this. But let's compute the norm square of this guy, so you can also see how this kind of space works, right? So the norm of J phi, and for that we start with that sort of phi, the norm square of this. What is that? So in this Hilbert space, that the definition of the norm is just the integral from 0 to infinity dt. And then the norm square of the value of the function at that time t. So that is the norm j phi, which is a function of t. We take that and take the norm squared in this space E. Right? Now, this, we can just plug that in. So this is j ct phi, j ct phi. Scalar product taken in E. But we know what that is. By the definition of the exit space now, this is a derivative, right? So this is equal to integral 0 to infinity dt minus d by dt of the derivative of this norm, but I have to, okay, I have to put in the vector ct, but I have to differentiate with respect to an additional shift, right? So I could say, yeah, but it's just this. Right? Okay, so this we take the derivative with respect to ct, but actually there's a small additional shift, and we differentiate with respect to that. But it's the same as differentiating this function. So this is an integral of derivative. We know what to do with that. So this is simply the value of minus the norm of ct phi square at t goes to infinity. That is the function here, minus this norm squared, minus the norm squared at 0, which is just the identity. And so, okay, minus, right? So these are just the boundary values here. Now, it's a contraction semigroup, so this limit actually exists because it's just going down, right? So we can just write it down, and this is also very easy. So this is equal to the norm of phi squared minus the limit of ct phi squared of t goes to infinity. Which exists, but it's in any case a number smaller than that. So this is a bounded number. Now that means that J is a densely defined bounded operator, right? So this is less than this, in particular, this is less than 1 pi squared, right? So it is a contraction itself, and therefore has a continuous extension to the whole Hilbert space. So although we define it initially just on this domain, it extends to the whole Hilbert space. This is why this notation is justified. It's an operator defined on the whole space. Now, what do we get here? Right? So any vector in the Hilbert space is now interpreted as a function of time, and we know this sort of space, right? So we have like in this kind of integration space, the sort of position observable is just the arrival time. But then we also have this additional degree of freedom given by the exit space, and that is where we can say what we are measuring at arrival. So actually, we'll see that the bounded operators on the exit space have a natural interpretation of observables upon arrival. And so we'll see how this plays out, for example, for a counter array and or an array of counters, right? So and various other examples where you see that this exit space naturally crops up, and it gives you exactly what you want, namely a description of what you can measure at an arrival event. So how does this work? When you have an observable on the exit space, how do you turn this into a joint measurement of something and arrival time? Well, that's very easy now. So let's say G is an effect, that is a yes-no measurement, let's say, for simplicity. So G is in B of H, right? So then the probability for arrival in some time interval and G clicking on arrival. Equals the expectation. So I have to write the joint event effect here, right? So this is the expectation of the following operator, right? So let me write GTS, something like that, right? So the expectation of this guy. Now this will be an operator in this dilated space, so I take, that makes sense like that, right? And GTS applied to a wave function, which is now a function of, let's say, a time variable. Let's call that one tau. Right, so this is equal to G psi of tau when tau is in that interval, and 0 otherwise. Right, so this is, if you take the space of E-valued wave functions as the tensor product of the time part and the E part, then this is just the tensor product of the arrival observable and the G observable. Right? So that's one way to write it. Okay, so we have these joint measurements of arrival time and thing that you measure upon arrival. So for example, several detectors that, let's say, M1 to, I don't know, MK, right? So these are terms for the Hamiltonian. And now, for each of them, I could compute an exit space. But then I could take the overall exit space for the, just as a direct sum. So E is just the direct sum of the EK. So that is, I have an observable in this overall exit space that just identifies the counter. So you'll see that this satisfies all the conditions of an exit space, because the normalization losses that I get from the different m's, they just add up to the overall normalization loss. So we have a sum of scalar products, and I can embed that into this direct sum. Actually, in some sense, so this E is a non-minimal exit space. And this is actually not what you get from the completion, but a dilation of it. So we combine the Nymark dilation here effectively with the exit space construction. So this is a non-minimal exit space. But it just gives you a possibility to combine detectors. Right? And that is the kind of modeling flexibility that I like about this. So the next example will actually be a standard example for the for arrival. Very often you ask, well, you have a confined, or you have a container in which the particles are moving, and the arrival will be an arrival at the boundary, and that is the next thing that we'll look at. Okay, so the situation that we want to look at is a region omega, let's call it, and that would be, let's say, a spatial region in R3. And our notation for the boundary. So there will be some kind of a regular boundary. And I'm not spelling this out. Piecewise smooth will be okay, right? So And our Hilbert space then is just the L2 of this space with standard volume integration. And what we want to describe with this is a free particle in omega with absorption at the boundary. So so it's just a standard free particle, and when it hits the boundary, it gets absorbed, taken out of the game. I don't know, whatever, right? So that is the kind of event that we want to compute the time for. And now there are two parts here. On the one hand, we have the free particle, so that is our generator for the time evolution is going to be what it always was for the free time for the free particle. So it's just the p squared over m, right? So and that will be the differential operator here. That by itself would be ill-defined for this boundary, because you have to say what happens at the boundary. You always have to say that. And you maybe have discussed a particle in a box at some point in your quantum mechanics lecture. And then what you would have to do to make this a well-defined problem and to bring in the box somehow is to state the boundary condition at the box. So for example, Dirichlet boundary condition saying that the wave function has to vanish at the boundary, or Neumann saying that the normal derivative vanishes. Now we do something different from that. Namely, our boundary condition will be that the gradient of psi, so the derivative, let me just put a vector on the gradient here, and then we take the scalar product with the normal. So this is the normal derivative. There are two normals you can take, like the inward normal that points into the region or outside. Well, our point of view here is that we really look for the particle, and we're interested in the inside. So let's take this the inward normal. And that is supposed to be now some function, so for x on the boundary, it will be some relation like that. And we take a minus sign here, then we'll see later the function lambda is going to be positive. If we want absorption, it would be negative if we have the opposite. And that of course, that sign will change when we change the convention about the norm. Okay, so I hope we'll get through with this. So let's see what kind of exit events we get here. Right, so for that, we just compute the scalar product of the exit space. So that would be like a minus d by dt of just a semigroup applied. That's the overall thing that we have to compute. And we already did part of this computation, so we get a minus I over h bar. And then there will be some constants coming from k here, like those. And then we have the scalar product of Laplace phi with phi minus phi with phi. So I just plugged in this expression for the Hamiltonian, or for the generator, and the earlier formula that expresses this in terms of that kind of imaginary part of the scalar product. Okay, so we convert that using something like Green's formula. Actually, I just use Gauss's law. That's easier. So we have like I over IH bar over 2n. Now this is an integral. This scalar product is an integral over omega. So and the integrand is the Laplacian of phi, complex conjugate, times phi minus this other combination. And I rewrite that as the gradient of something, namely, the divergence of something, namely the divergence of the vector field, that would be the gradient of phi, but complex conjugated, times phi, minus phi bar, the gradient of phi. Now, if you just do the computation here, then you see that the gradient acting on this part will just give the Laplacian. That's why we have a scalar product here. And the second part, where I take the gradient on the function, or in this case on the complex conjugate, that will just give two terms that cancel. So we can apply Gauss's law. First of all, we can apply Gauss's law. So this is going to be I h bar over 2m. And then there will be, let's just write it, the integral. So this is the surface element there. So the surface element is in the direction of the normal. Right? Now for Gauss, applying Gauss's law, the convention is that you take the outward normal. Now we take the inward normal. So we put a minus sign here. And then we have just this expression that we had before. So this is in the direction of the inward normal now. And we have the gradient. So we get just the absolute value of that. And then minus I lambda phi complex conjugate times phi minus the opposite thing, okay? So we have a minus I and a minus I complex conjugate. They cancel, so we get the lambda. And actually we have two equal terms that cancels the 2 here. So we get h bar over n. The integral over just the scalar surface element times the function lambda of x times what is left here is the phi absolute squared. And this is an integral over the boundary, right? So here, after this is an integral of omega, this is an integral over the boundary, and of course this is an integral over the boundary. Okay, so this is our final formula for computing the exit space scalar product, or the exit space norm, and we can always get the scalar product out of this. So, in other words, we have computed the exit space, so let me write it down. So, in other words, the exit space is the following. We can just see from the scalar product there. It's the L2 space on the boundary, right, of functions that live on the boundary with the measure df. Well, there was an h bar over m also, and times lambda of x, something like that. Huh? So this is the weight with which we integrate over the boundary. So the boundary conditions directly go into how the scalar product has to be defined. Of course, that's the absorption process that goes into it, and so we should make that. This could be different in different parts of the boundary. Actually, it could be 0 at some places. Then it would be Neumann boundary conditions at that part. There would be no absorptions at this point, right? At such points, and so on. So you can also make it make Dirichlet points that look a bit more complicated in this language, but you could also do that. Right? So, but now think of the interpretation that I gave. Right? So the exit space is that Hilbert space in which you describe the observables upon arrival. Well, here it's just the position. You immediately see the position observable on the boundary, and that will give you the hitting point. Right? So you get a joint description of not just the arrival time, but also the arrival place. This automatically is in the same formalism. Okay.